I'll put it all in. So L M. So that you know you're talking about the associated Legendre polynomial, right, with two parameters, L and M. Now it's just a weighted sum, right? So let the highest power of we're talking Z now, right? So this associated Legendre polynomial is a weighted sum of powers of Z. So let the highest power be n, right? Integer n. So you've got Z to the n is your highest power in this polynomial. So what is the highest power of Z in the equation, in the associated Legendre equation? Well, it turns out to be Z to the n plus 2, and I've asked you to do that for homework. Why is it? Well, I could give you a hint. In the associated Legendre equation, there's in the denominator there's a 1 minus z squared, and so if you multiply both sides by 1 minus z squared, that z squared helps get you this plus 2. So the highest power of z in this equation is this form. That's your highest, right? Now remember, it's an equation, and you're solving it by using a weighted sum of powers of z, and the coefficient of each power of z has to be 0, right? Because the right hand side is 0. So that means, and that's for all powers of z, and hence all coefficients of those powers. So all those coefficients have to be 0. Well, what's the coefficient of this highest power? Well, you can work it out. It's not too hard. It ends up being this. All right. This is the coefficient of this highest power in this equation. The highest power of z. It's this, and therefore this here, because all coefficients have to be 0, so this coefficient of the highest power also has to be 0, and therefore you can solve for lambda. Okay. So lambda is just n times n minus 1 h bar squared. Alright? Now this is a bit inconvenient with this minus, so let's define L such that n, the n's here, equals L plus 1, so you just got an L here. So your lambda now is just L into L plus 1 h bar squared, and therefore your L can range from 0, 1, 2, dot, dot, dot. So the non-negative integers. Okay? And you've seen this sort of thing before. So now we have constraints on lambda. And remember, lambda is the eigenvalue. The lambdas are the eigenvalues of the square of the total angular momentum. So it's L squared. Right? And those, the total angular momentum is quantized, right? Because these L's here are integers, right? So the angular momentum is quantized. Very important, right? Quantum mechanics, quantized mechanics, right? So here it is. So the angular momentum is quantized. All right. Now, if you square the z component of the angular momentum, common sense says that cannot be larger than the total, the square of the total angular momentum, right? A component of something cannot be larger than the total vector, right? So that implies that m squared is less or equal to L into L plus 1. Where does this come from? Where does this m squared come from? Well, now this is expectation value, right? So the L squared operator, if you plug in the eigenequation, so this is shorthand for psi, bra psi operator, ket psi. So L squared z of of the psi, will give you m psi. It's the eigenequation for the z component. And you got it twice, so you'll get m squared. So you've got this m squared cannot be greater than. In other words, it's less or equal to this. And what's this will be the eigenvalue of this is lambda, okay? But lambda is L into L plus 1, so you get this sort of stuff. Now L's are integers, M's are integers, and for this to be true, M has to be in this range. So here it is. We've got this again, right? We've got it again. Now this was physics, because we're talking about eigenequations and so forth. But we got this result earlier, just out of the mathematics, right? So, like I say, this condition emerged naturally from the solution of the associated Legendre equation. Right? Here we've deduced it from physics, but we also got this from the mathematics. It dropped out. It was derived naturally from the mathematics. So we've come at this result from two directions. One the physics, the other the math. Okay. So the solutions then to this associated Legendre equation, you can label them, and this too is revision in a sense, by the eigenvalue lambda, which is the eigenvalue to L squared, the square of the operator of the total angular momentum, L, okay? And the other parameter, so you can label it by two parameters, and the other is the eigenvalue M, which is the eigenvalue of the z component of your angular momentum, okay? And so the solutions to this are your associated Legendre polynomials, right? P, L, M. So you're getting this expression from physics type reasoning, and we also got it from the math, of course. That's what Appendix B was all about. Okay. So these are the solutions to this, and if you multiply them by the phi term, e exponential to the power I m phi, that creates a spherical harmonic. Okay. And from the spherical harmonics you can calculate the polar plots, and you'll get all these wonderful weird shapes, these lobes, and we'll be talking more about that, because now we're bringing in angular momentum into physics, into quantum mechanics, and then we will be able to now finally discuss the Schrödinger equation, the full Schrödinger equation of the hydrogen atom. And we won't restrict ourselves to the spherically symmetric wave functions, the inner ones, for the probability distribution of the electron, finding the electron in the hydrogen atom. We can now start talking about angular momentum. We get all these lobes, and things get more complicated, but more interesting. Run out of boards, so till next session, next board.